Is your coffee ready? Mine is right here. Welcome back to another amazing paper. This time we're going to talk about this one called Learning Indoor Inverse Rendering with 3D Spatially Varying Lighting from these guys from NVIDIA, University of Toronto, and Vector Institute. The basic idea of this paper is to take an image and split it into 4 components. Albedo, which denotes how bright a surface is. 0, meaning it absorbs all light, and 1, it reflects all light. Also normals, depth, and this one, lightning. Those are pretty common and classic representations, and also this problem is a pretty classic problem in computer vision of intrinsic decomposition of an image. And the novelty of the paper comes more on this end here, the lightning representation. But why using this representation? As the title says, it allows you to render from many different points in the scene. So that's where the 3D spatially varying lighting comes into action. Meaning that, for example, in this image, a render on the left will be different from a render on the right. Here you can hopefully see the armadillo reflection on his chest is brighter than the one on the chest of the dragon, since they are over different surfaces. It's not the first paper that enables this kind of render, but it's one of the most realistic ones, since you can do this kind of rendering, spatially varying, and also have high dynamic range, as you can see here projected on the wall the shadow of the sphere. And also you have high frequency information if you have a reflective object. So this is a pretty exciting paper to read because it allows you to do these 3 things at the same time. Also, another neat aspect of this paper is that it uses inverse rendering. And the best aspect of this is that it makes HDR image unnecessary. Why? Because by rendering all the predictions, they should get to the original image, which means having all lights effect of the input as well, as I will be seeing in the next few minutes. So let's understand better how they propose to represent light. In their case, what they come up with is this volumetric representation called volumetric spherical Gaussian, which is a voxel-based representation where each voxel has a spherical Gaussian in it. And it's represented by these parameters here. Alpha, which is an opacitive, so from 0 to 1. There's the intensity, HDR RGB, so 3 values. There is mi, which is the lobe axis of the Gaussian, and sigma, which is sharpness. So taking those parameters here and a given angle, you can have the color of this given voxel by this formula here. Now, if you want to know the color of a given point in space, let's say here the point which basically later will become the pixel of a picture, what you can do is you can trace a ray in the voxel representation, the VSG, and it will intercept those voxels, and basically, let's say here, and then to intercept some points here. And what you can do is use this formula here, which will take all those voxels into account and apply the alpha and all the values for the equation that I show above, and put them together, and basically you have the final color of the pixel using this formula here. And also, if you can also have this equation by replacing the spherical Gaussian with the depth, and then you can have the depth of the scene, which is also quite nice. Now let's see how they propose to estimate all of this. So here is the basic overview of the model, and it's divided into 4 sections. So at first there is the module called Direct Prediction. What does it do is to take a ResNet and give a first estimation of albedo, normals, and depth, and a lightning global feature. So this one is taken further to another module called Lightning Joint Prediction, which has another network that outputs the final voxel VSG representation. There's also another module called the differentiable re-rendering, which will take these predictions and the lightning and it will re-render the scene and try to approximate the input. And finally, there's a fourth module called the albedo normal depth or joint reprediction module, which will take those here and try to make it to optimize them, taking the error from the rendering into account. So let's see each one in detail now. This module is quite straightforward, as I just showed. It's a ResNet that takes as input an image and output three images, one for the albedo, one for depth, one for normals, and it also outputs a global feature vector. So it's that's all it does, and just gives it to the next modules that I'm going to explain. For the lightning module, what we actually have is two different sources of information. So the first one is the vector, the global feature vector FL that was in the picture. You take this one together with the 3D position of a given voxel and you provide it to an MLP decoder. And this MLP decoder will give you this another feature here, ZG, and with that you can compute what they call the scene global feature volume. So this is done for each and every voxel on the volume. So the next part of the information is the visible field of view of the image, which has a lot of important information, so it's really useful to use it. So what they do is to unproject this visible field of view information and provide this information to a 3D unit. So given the predictions of depth, normal, and albedo and depth, if you back project them into the pixel from a pixel point to a voxel, you can basically have a local feature, what they call, by concatenating all this together. So they take the input image pixels, normal, albedo, processed, and they multiply by k. And k is this Gaussian distance from between the voxel and the corresponding pixel. And also they have this sigma, which is a hyperparameter, and by doing that they have this local feature, and all these local features, they are called visible surface lighting volume, and they take those two features together, so the global and local features, they fuse them and they give again to another 3D CNN, which give us our final lightning volume with this dimension here. So to glue all this information together in order to make them coherent between each other, so to be able to regenerate the input image, what they propose is a differentiable ray rendering module, which is based on a Liberation reflectance model, and it takes for a given pixel its position, and so on image space and the depth, and they also take the albedo normals, and using this equation here for the Lambertian model, they can reconstruct or they can render and have the final color for a given pixel. And to make this all differentiable, they have this soft clipping function, and they can use their re-rendering procedure to optimize the whole system. Finally, there's this joint reprediction module, which takes all the predictions so far, and it adds another information, which is the error between the input image and the image that we just re-render. And it also takes shading, which, as I say, indicates how albedo changes after the re-rendered image, and also the Jacobian of the shading. So all those informations together combined are provided to a network, which takes also all the predictions that we already mentioned before, the albedo, depth, and so forth, and it generates a final prediction for albedo, normal, and depth. And so that's the method. So for training, they have this synthetic data with ground truth, input image, albedo, normal, and depth. And the interesting part here is that the panoramic image are all LDR. So they have a pretty nice data set, or easier way to get a data set because they don't need HDR information given their setup. And their loss for training comes from two parts, as I say, direct supervision and the re-rendering loss. So let's take a look at the direct supervision. It is quite standard in the sense that, well, losses, normal losses as L2, L1. So for albedo, what they have is L2, and they also have another constraint, which is the gradient of albedo to be locally constant. For normals, they have the L1 angular error. For depth, they have this log encoded L2 loss since the depth is high dynamic range, and also they have another L2 to encourage relative consistency. And that's one part of the losses. So for the lightning, what they have is a photometric loss. And since they have the ground truth, albedo, normal, and depth, what they can do is to render novel views of the scene and compare that to the rendering using their lightning prediction. So in here, what you have is this, you have the pixel P, you have the camera pose, the camera intrinsics, and then you can do you can trace the ray starting from the camera into this direction R, and then to render the novel view using their prediction, what you use is the equations that are shown above in the paper, and you can have again a render of the scene using the predicted light. And to train the system, what they use is an L2 loss and also an adversarial loss. They also use another approach, which is consistency with the visible field of view. Basically, what it means is they want to make the input image I and depth D as close as the ground truth as possible. So they use L2 loss between I and D and the rendering respective RGB image and depth using their lightning volume. And finally, for the re-rendering loss, it's basically L2 between the reconstructed and the ground truth. And as the authors say, this is the part where you can go from LDR to HDR, since the dataset is all LDR, so there's no explicit forcing of HDR up to this point, but with the re-rendering loss, it basically forces the method to compensate for all the physical aspects of having light in the scene, which are not possible to be reproduced if you have LDR. So the network at this point learns the HDR lightning. For the training, they go into a step-by-step training. So they start by pre-training the albedo, normal, and depth branches, since they claim that those are necessary to be learned before the lightning prediction module can operate, because it depends on those. So it starts with that. Second point, they keep training these branches here with the lightning prediction model, so this is the second step. And finally, once they are trained, we freeze their weights and train the reprediction model for albedo, normals, and depth. And at the end, we find the authors, well, everybody that used the model, fine-tune all the three modules end-to-end with the multitest loss. And then we get the final albedo, normal, and depth. And now let's see some experiments, exciting part. So the authors used throughout the entire paper a dimension and a VSG of size 128 by 128 by 128. And they say even though it seems big, it's much lighter than Lighthouse since it has 6 3D UNet subnetworks. And it uses 7.5 gigs of a GPU to do all of this computation. For training, they use the interior net dataset, which is a synthetic dataset with many indoor scenes from houses. And in their case, they render 1,000 LDR perspective images on each sequence with albedo, normals, and depth, and 1,000 panoramic images from the corresponding viewpoint. So this is their dataset. So for results, they compare against these papers here, SIRFs, which is one of the classic optimization methods, NEAR and Lighthouse, which are more recent, and they show many results on each individual prediction and also in the combination of them. So talking about albedo, normal, and depth on the interior net dataset, they have also an ablation result where they remove the joint reproduction module and also have the joint reproduction but without the lighting part. But finally, by doing all together, that's where they get the best results. Also here they do the evaluation on the interior net, and it gives an idea about the peak signal to noise ratio. So by combining all their losses, they get the best result. And here it's a result where they compare their representation with the spherical Gaussians in comparison to a classic render where there's no render with the spherical Gaussians, and they show the difference and how important it is. In here they have another evaluation on the albedo using the weighted human disagreement rate, since they have a notation for the albedo made by humans, and in their case they get again the best result, and showing that the joint reproduction module makes a difference on the results as well. Here they have some results for normals and depth on the NYU V2 dataset, and both for angular error and depth they get better results. And in table 5 they have results for the re-rendering error, and this one is interesting because it give us an idea about how close they can get to the input image given all their predictions. So they have some ablations to the studies here as well. So first they remove the re-rendering loss, they remove the spherical Gaussian, and they let it for the classic rendering procedure. Also they have the complete method and another one where they train with real-world images. Curiously, it doesn't perform better, but anyway, it's the closest one to the one that gets the best result. And also results for the NYU V2, they get the closest of all the methods. Here we have some qualitative results, basically for the albedo, normal, and depth. And you can see that their model approximates quite well all the individual parameters. But honestly, I would say it's hard to see a difference between this one without the joint reproduction and the full method. But as we saw earlier, the numbers show that there is a good difference, but here on the images is quite hard to see, in my opinion. Also here on the bottom we have other albedo normals and their final re-render image, and those are also on real images, and it's basically a comparison to NEAR, and you can see that they get a better approximation and rendering compared to the ground truth. And here renderings, my personal favorite part. So they compare to other methods, the NEAR, Lee, and Lighthouse, and as you can see here, well, their renders are good in the sense that they have an overall idea of the light position, but the problem lies mainly on the reflection on the sphere, as you can see. And let's say Lighthouse is the one that gets a better reflection, but it doesn't give you HDR information, so there's not much shadow being projected on the wall. Meanwhile, the method that we are talking about gives you both the high frequency information and the shadows on the wall, which is really interesting. And finally, we have also renders in different locations of the scene. And again, the same pattern occurs. You have fairly good amount of information about the lighting, but the reflection itself is not optimal as the one that they propose. And they can move the object around the scene, and it gives you a coherent lighting and reflection on the object. There's also some other results here on the bottom where they simply insert objects in the scene, so you have a feel of how their prediction helped on the rendering. And as you can see, the objects inserted in the scene, they blend quite well, and they give you a nice feeling of them belonging to the original scene. All of this made automatically, and since also they get depth, I'm not sure if they project this on the shadow catcher or it's using their depth prediction, but it shouldn't be hard to use their own depth prediction to make those renderings directly, so you don't even need to worry about a shadow catcher and find the camera parameters to insert a 3D object into the scene. So this is pretty cool. So I hope you enjoyed this review and stay tuned for next papers. Thank you.